All right. Today I want to start our discussion on radio and Wi-Fi wireless communication. There's quite a bit to it, and we'll only be able to sort of scratch the surface of it. If it sounds really interesting, then you really should take some of the classes in the ECE department, where they can spend the whole semester on antenna design. We're going to try to get a rough idea of how things work in wireless and in Wi-Fi. So in order to think sort of reasonably about wireless transmission, I think we need to have some idea of just how the medium works. So we're kind of getting into the physical layer a little bit, like at least what the physical environment is like for a radio signal. We'll talk about how actual transmissions in the physical layer happen later on, but we need to have some sort of idea of how a signal propagates in space, basically. So first off, I wanted to talk about decibels. You've probably heard of decibel before, probably in a sound context, right? Decibel, then it's dBA, I want to say. Actually, let's look this up. dBA, decibel. Right. So 60 dB, we say decibel, but it's short in this case for dBA, which is sort of, I don't know if it stands for audio or ambient sound, or it says A weighted here, but what's that supposed to mean? What I mean, yeah, okay. So I don't know what the unit A is in the sound scale, right? But we know that, say, 100 decibel, that's a screaming baby in your ear, and 25 decibels is like a pine needle dropping on the floor, sort of thing. Turns out that decibel, deci is 10, right? And bell is I don't know why it's bell. It's only a factor. Right? So here we're saying, oh, dBA, that's something to do with sound. In radio transmissions, we talk about dBm. Oh, so dBA, sound levels. dBm, that's decibel milliwatts. Oh, watts. Come on. Okay, so what is all this decibel? If you have a value x, we can write it in decibel instead. So this is a unitless value x. The decibel value would be 10 times log 10 of x. So if I say 100 milliwatts, right, that is the same as log 10 of 100. What's that? Anyone? 2. All right, good man. So then, that means it's 2 times, and then there's the 10 here, right? 10 times 2, 20 dBm. I think it's like that. It should be properly with a little d, I think, and a big B, if I'm not mistaken. Okay, so we use decibels because it's annoying to deal with very large numbers when we actually don't care about anything except how many zeros there are. Right? How long the number is what really matters when we're talking about enormous scales. And that's what decibel is for. So let's look at a few more examples. So a transmission of 1 milliwatt, right? Log 10 of 1, that'd be 0. right? So 10 times log 10 of 1, that's a 0, I'm pretty sure. Okay, let's try something a little bit larger, like your microwave oven. That's a kilowatt, right? So that's 1,000 milliwatts, 1,000 milliwatts. So what's that? Well, so a microwave oven will be about a kilowatt, which is 1,000,000 milliwatts, right? 1,000 kilowatts, 1,000,000 milliwatts. So basically we're counting the number of zeros here, right? So this will be 60 dBm, right? So this is just to give you an idea of how, like the range of decibel values. Okay, now unfortunately with radio, we don't get to receive dBms, like integer value dBms. That's already quite a bit of power. If you can get a milliwatt out of the air, you're probably not in a healthy spot. Right? You probably want to step away from the antenna. So we end up with negative values. But so you can, at the same time, if we say 0.1 milliwatt, that's minus 10 dBm, right? And so on. Minus 30 dBm. Why am I talking about all this? Well, we'll see in a little bit. These sort of scales of numbers are important to have a grasp on to understand what's really going on in the radio environment. Okay, so there's some idea of how a decibel works. I think a good way to think of it, a factor 10 in the real value is plus 10 in decibel, right? And a factor 2 in real value is about plus 3 in decibel. That's weird, but that's how it goes with logarithms, right? So now if we want 1,000, it'll be 10 plus 10 plus 10, right? So there's 30 dBm. Okay, so what's really interesting about radio environment is that what you send really is not what you receive. Right? In a cable, you put in a watt, you get out pretty much a watt, except for some heat losses in the cable. Right? If you put in what you usually would transmit in Wi-Fi in, let's see, typical power levels. Your laptop Wi-Fi might send maybe call it 13 dBm, something like that. So we're sending about, so what is that? Right, about 20 milliwatt. You might send you might get up to maybe 20 dBm or 100 milliwatt, right? But it's in that range. We're sending in the 10 to 100 milliwatt range about. That is not to say that the radio uses that much power. It'll probably use a little more power. There'll be some losses in the device. But sort of what's radiated out from your laptop is something like that. So then what is received by the wireless access point? It all varies. If you're close to it, it'll receive more power. If you're far away, it's less, right? But sort of a not unreasonable power level that's received would be on the order of minus anyone want to take a guess? It's got to be in the minus, because otherwise it's just really a lot of power. So let's see, 0.1 to, so then it's not minus, then you always get positive real value. So 0.01 to 0.1 milliwatts, we're saying, right? Okay, that's a fine guess. Anyone else want to take a guess? So here let's see, so we lost about, what is that, 100? We got about 100th or maybe 1,000th of the power that was transmitted, right? Yep. Nobody's seen these numbers before, anything? I think it's pretty cool stuff. Okay, so actually, this is a guess. We're talking about minus 90 dBm. It can go down to minus 96, I've seen, for a really slow sort of Wi-Fi. And you can go much lower than that for these long-range radios, but they get really slow. Okay, minus 90 dBm. What is that? All right, that'll be 10 to the power of minus 9 milliwatts, right? A billionth of a milliwatt. And we sent out 10, say. So so you're going to end up somewhere between a billionth and 100 billionth. Let's see, a 10 billionth and a 100 billionth of the power that was sent in your normal transmission to your home access point. So, okay, so where did all the power go? Like the general idea of how radio transmission works is it starts in a point, right? Let's make this simple. It's not, and then we'll look at radiation patterns maybe, but let's start from a very simple point of view. There's a point source, right? My source antenna, and it goes out. The transmission, I send a bit, like the power of the bit starts out being 10 milliwatts, and then it's always 10 milliwatts, but it's in a bigger and bigger shell, and it travels out at the speed of light in all directions. And then somewhere, there's a point receiver. It can't really be an infinitely small point, because then you receive an infinitely small amount of power. So let's have some surface area of the receiver. It's up here. It's looking at this sphere. And you have this little receiver, and it picks up the power that meets that sphere. Sorry, not the sphere, that meets that little area of the antenna. Yeah?
So it's not like directed, it's like kind of...
Yeah, it's not at all, well, so it all depends on the antenna. Then there are clever ways to try to direct the power. I don't think that there is any directionality in your laptop except for accidental. So the simplest model to think about, at least, is this: it goes out in a sphere. So then it's kind of, let's see, I think I had a neat picture of that. Yeah. All right, so here it is. So now the surface of the sphere, right? We don't care about the volume of the sphere, because the bit is only available to the antenna in an instant, right? And then it moves on. So the power isn't wasted here, and it's not wasted over here. It's just kind of, it goes there, and then it passes, and it's gone. So it's the power is spread out over the surface of this circle. So if we start out with the size of our original antenna, let's call that a little ball, right? And then it grew by some amount. That sort of the ratio between our the size of our initial source and the distance, like the sphere at the distance at the receiver is at, that is a large part of the loss. Because we sent this stuff all over the place, and there's only this tiny receiver over there that's picking it up. Yeah.
So is the fraction that is like being projected, it's proportional to the distance also, right? So is it like you have a...
Yeah. So it's exactly like this, right? So the received power will be the source power divided by 4 pi r squared, right? That's the size of the sphere at that distance. It gets bigger the further out you go, right? So, okay, so this is a very important part of the loss. Yeah.
Oh yeah, when the connection is made, can the router or the laptop do anything about? Like, I know where my connection source is now, so I'll try and like optimize the.
Excellent question. So I guess first of all, I should point out that there is no such thing as a Wi-Fi connection. Like from a physical point of view, it's only a logical connection. In that there's been some agreement that I'm going to listen to your stuff. It's possible with a sophisticated base station. This one may have more than one antenna. It might have maybe 4 antennas inside of it, and those 4 is called multiple input, multiple output, MIMO. They can sort of synchronize their transmissions on 4 antennas, so that kind of lines up constructively. I think we'll skip interference patterns in this class, but there's ways to kind of steer the transmission a little bit so you get some more power in the direction that you wanted without turning anything. I should, let's look at a couple of antenna types. Okay, so sometimes I forgot to do that. So there's a typical Wi-Fi antenna that you might have seen on your wireless access point at home, right? Screw it in. Basically all that's in here is one cable that goes straight up. A dipole antenna, it radiates horizontally. So if you take this antenna, say this is the antenna, it's pointing like this, then it kind of radiates like that and down like that and in a big circle all around. So funny enough, if you try to point the antenna at your destination, you're actually giving it the least signal you can. And you have that's the null point of this radiation pattern. It's not quite that bad because you can't be that precise. The antenna itself might do that, but there's all sorts of reflections and stuff. We'll see in a minute. Okay, so dipole is very naive, but it's nice, simple. And let's see, there's a couple of nice directional antennas. I'm sure you've seen these. They're not really used for Wi-Fi, but if you want to pick up a satellite transmission from 20,000 kilometers away out in geostationary orbit, more than 20,000 kilometers away, but something like that, then it's good. These things can have a gain. I haven't talked about gain yet, but they can have they can improve the signal received by an order of 1,000 or so compared to a dipole. A dipole antenna is sort of the simplest thing you can have. The bigger, naturally, the bigger the dish, the more of the radiated power. You know, it's this circle, right? Everything's going out in a sphere. The more of the sphere you can sort of capture, and you see it's bouncing off of here, and you make the shape just right for the frequency you're transmitting at, and so on. And it bounces in and concentrates here, and the actual receiver is here. So there's a normal radio receiver sitting over here, and this is just a big passive reflector, like a mirror for the radio waves. There's a couple other ones you probably have seen. Those are common on all over the place for point-to-point links. You want to have a transmission between your cell tower and the next cell tower. You point 2 of those at each other. Now the transmission from the point source, which is sitting over here, it starts out as a sphere, but then it encounters this grid behind it, right? And the grid takes all of that energy and bounces it all together toward the destination you're interested in. And same thing on the receive side. It takes all of that energy, bounces it toward the antenna, and kind of concentrates things, and you can get an improvement of something like 100. Let's see, 24 dB is the best one I've used. So 100 to 200. 1,000 is 30 dB. 1,000, yeah, you could maybe get to 1,000. That's a really big one. But that's on each side. So you put another one on the other side, you get another 24 dB of improvement. Okay, so I want to show you a dipole radiation pattern, just to see what it kind of looks like. So here, let's not have a movie for a simple thing like this. Okay, which one do we like? I like this one. Right, so it'll look like this. So here we are, the antenna is like this, right? We're looking at a cross section of the transmission pattern. So it's kind of radiating out like this and like that, and not so much up, right? It's more like this, and then all the way around. I don't know what's going on over here. Okay, so right. What about the frequency? Wi-Fi we're sending at about 2.5 gigahertz. That's the normal Wi-Fi 802.11b and G. They will send at 2.4 gigahertz, and then there's a 5 gigahertz version, the A. There's no significant difference between the two, but what does this mean? Like these gigahertz, what's all that? Well, all transmissions in radio kind of looks like sine waves. They're kind of modified in various ways, but the basic shape of a radio transmission is a sine wave. And so now the hertz says how many times does it go like that? Start from 1, go all the way around, and back up. So 2.4 gigahertz means that in 1 second it's gone up and down 2.4 billion times. And so speed of light being 300,000 kilometers per second, we can divide the two and figure out how long that is. Actually, let's do it. So 300,000 meters. Okay, a meter being like that. Divide by 2.4 billion. Did I get that right? Yeah. Okay, so this is in meters. So that's 12.5 centimeters. That's actually almost exactly 5 inches. Right? So about like that. So a Wi-Fi transmission, it'll go like this, right, in about 5 inches. The reason it becomes 5 inches is it moves really quickly, right? So 1 bit is many more than this, but at least the sort of the basic shape is that size. So if you have a hole somewhere that's about 5 inches, it'll travel through that without any problem. If the hole is smaller than 5 inches, depends a little bit on the material, right? But it'll probably start obstructing the Wi-Fi signal. If you have a sort of a cage of copper and all the little holes are like 1 inch or something, probably you're not getting much signal through at all. So that brings us to the microwave oven. Microwave, actually, the oven transmits in a similar way. It transmits in a 2.4 gigahertz band, which is unfortunate. But it has a cage around it on the inside, a metal cage. So it transmits at, what did we say? 60 dBm, right? But only a little bit makes it outside, because there's some little gaps and whatever. You probably don't want to put your head against the microwave oven, but it's not the end of the world. People are worried about Wi-Fi transmissions, like, oh, I'm going to get cancer from the Wi-Fi thing, and then their neighbor is using a microwave oven. And probably they should worry more about the microwave oven, because it's 100 million times stronger, right? So, if you have a little hole in your microwave oven, that's a problem. Okay, anyway, so that's part of what's going on. We are transmitting, actually, see if I Oh, no, that's good. So we transmit an initial signal. It kind of goes out. We try to change it a little bit with antennas, with clever antennas. We kind of make it not go completely all the way. It'll maybe be more like a triangle going out. And unfortunately, it's still proportional to the radius squared. No matter what you do, it's going to be, unless you have something that looks like a laser, it's like really straight, just a line. It's always going to, you're going to have path loss that's proportional to the square of the distance. Okay, so what else is going on? You may have noticed other effects with Wi-Fi, right? Distance is an important one. What kind of antenna? Yeah, you don't really run into that because you don't get to change the antenna much. What else affects Wi-Fi?
Like physical objects.
Yeah. Okay, something in the way, right? So if something gets between you and the radio, how does that change the signal? Well, it gets weaker, generally speaking. If it's, say, a piece of paper, it probably doesn't affect it very much. But if it's something more substantial, it'll affect it more. How much? I found a nice, let's see. This is called attenuation. So one is path loss. It's distance, basically. It's just distance. It's path loss. And then there's attenuation. That's when you go through something. So some general ideas, right? There are no people here. Do we have any bags of water? No. But okay, so going through a normal wood door, 6 dB, right? So you lose about 4. You go to a quarter of your signal, right? Going through a wood door, you're down to 1/4 of your signal strength. At another wood door, it's another quarter, right? So now you're 16th, right? So you probably don't want to have too many things in the way, but it's not as bad as it looks because we started out with like 10 dBm of transmission power. And the distance is only going to be a part of that. So we still have probably some, we can afford to lose a few of these. But if you have a lot of these steel fire exit doors, like, what is this? 20 dB losses, it starts getting kind of grim. So you might in fact, we'll see this later, but when you, the link, it automatically negotiates how fast to transmit. If you only get minus 95 dBm of transmit power through, you have to go slow, right? You say everything very clearly and slowly, and we'll see exactly how later on, but you really have to go slow, so you're down to 1 megabit per second, and if you're lucky, you don't have any path losses. Any packet losses. Then you open the steel door, and now you suddenly got 19 dB better. 19 dB, how much is that in factor? It's almost 20 dB, right? 20 dB is 100 times, exactly. You open the door, you got 100 times better transmit power or receive power, and that'll probably translate to also something like 100 times better data rate through. Okay, so there's a big factor. We have the path loss, we have your gain, that's the antenna shape, really. Like how much of the signal do we get to collect and how much is going out in other directions. And then we have your attenuation, what's in the way. And things like leaves of a tree are a huge problem because water is very good at catching 2.4 gigahertz transmissions. That's in part why we use the microwave oven in that frequency band, right? It heats up the water in your food. So leaves are a big problem, clouds are a big problem. That sort of thing. People are a big problem. So this is interesting. You try, you're a wireless technician, you're trying to set up your Wi-Fi system, preparing for this big conference. You try it in every location. You set up all these antennas, you try it all over, it's beautiful, it works so great. And then the room is full of people, and then even if no one's got their laptop open, it doesn't work so well anymore because you have all these ugly bags of mostly water attenuating the signal in all directions. Okay, so that's That's one, like attenuation is one problem. Another problem with this crowd being there. Any ideas? Well, actually, I said that they had their laptops closed, but let's say they opened their laptops. So now,
all these devices are trying to connect on the same frequency.
yeah, so forget the connection part. This is sort of the connection is maybe more of a logical thing, but in pure physics here, if there's some other transmission going on in the 2.4 gigahertz band, it sounds like noise. So you're having a nice conversation, and then come some other noisy people, and they start making noise. Well, now you can't really have your proper conversation anymore. You have to start getting closer to each other, shouting in each other's ears, right? And, right. So this noise works the same for radio. It's okay if you have a little bit of noise. You can kind of deal with that, but you get more and more noise, you get less and less of actual useful signal. In fact, it's a plain subtraction. So if you have 10 dB of noise, actually that's too much. But if you have minus 60 dBm of noise because there's a nearby transmitter, right? And then you're trying to get your signal through, and you have maybe minus 50 dBm of signal because you're really close. Well, now you actually lost part of that because we lost like 10% there, right? Because we had a 10th as strong noise transmitter at the same time. So you have to kind of subtract that from your link budget. And that was the next part I want to show you. Yeah, let me just pull this up. All right. Yes, question.
So, do the waves, when we have attenuation, the waves still pass through the object, right? Or they're just weaker?
Yeah, so we haven't discussed multipath yet, but yes, the waves will pass through most objects.
So I was kind of wondering, how do the dishes work if the waves pass through the object?
So I guess if it's a sheet metal door like this, and your receiver's on the other side, it doesn't pass through it. But if it's a wood door, it'll go through, much of it will go through, and some of it will end up heating up the door. So the antennas are made of a material that catches all of it, or reflects all of it. With these grid antennas, it only works because remember the wavelength is like 5 inches. So as long as the holes are about half of that, it'll get most of it. I'm not familiar with exactly, like, if you have square holes, like how much of the power comes through in the corners and things. But it's something on that order. Okay, so generally speaking, if we have a clear line of sight, we transmit at some power, 10 dBm, right? We lose a little bit in the cable. It's actually true. If you look at the cellular towers, like a proper tower now, you can see the cables going up. They're these big, fat, black things, right? All it's doing is transmitting some, like, people's voice communication. It would be enough with just a little Ethernet cable. But they have these big, fat copper cables going from their electronics, which is in a box on the bottom, up to the antenna. And the reason is they want to lose as little power as they can in the actual cable on the way up. So they have very low resistance, good cables going up. Okay, and then we have an antenna. If it's a point source that goes in all directions, that means we have no gain. It doesn't help at all. But usually you will have a little bit of gain. In that gain meaning we didn't waste stuff going straight up. We sent everything like that. And so the power that should have gone straight up, it went this way. We get twice as much going this way. And that's in a dipole antenna, one of those sticks. You could expect a gain of maybe 2 dB. Here we don't have to talk about dBm, it's just 2. Because we get like twice as much power in the direction we want. There's no unit, it's just twice. Okay, and then there's the distance. And because it's all proportional to the... Now, we already kind of calculated in the change of the shape of the transmission here. So now it's just a distance straight. So divided by 2 pi r squared, right? There's your distance, your loss for the distance. And you'll have to, depending on which unit you have, like meters or feet or miles in this case, it'll be a different constant over here. And then finally, receiver gain, 2 dB again, because we had another dipole there. We have something else on this one. And then cable loss. And then now we see how much power did we get on the receiver end. And if we got enough for the lowest data rate that our receiver supports, and we ended up transmitting at the lowest data rate, transmission has to be slow, and the receiver has to be able to understand such slow transmissions. If it's enough, and there wasn't too much noise, actually you should do like minus, or there's a loss here, so we say plus noises, plus noise level. If there's enough after all of those losses, then we're good to go, and we can receive the signal, generally speaking. There's one more thing going on. It's a little more complicated. It's called multipath. So, and that can be helpful and can be hurtful. If you're trying to transmit through this steel door, right? Nothing's going to go through the steel door, but it might go through the brick on the side of it, right? Now, if your receiver is on the other side of the steel door, it doesn't help that it goes through the brick because it's going to miss. But there's something behind there. There's like a water cooler or something. And the signal will also bounce on whatever's behind it, right? And come back. So, and it'll bounce on everything else. It goes in all directions. It just bounces in all directions. And then all these signals kind of add up, sometimes constructively, meaning like they were off by a little bit, right? The signal goes like this, but then it bounces, so now it goes like this. If they add up like this, that's destructive. So now, like we have a bottom of the sine wave and top of the sine wave, add them all together, the mean is nothing, so we didn't get a signal. But if we get lucky, you get a bounce and they're together. Now that's constructive interference, and then it gets better again. Yeah?
So I'm kind of confused on when does the signal pass through something and when it bounces off something.
Yeah, that's really confusing. It's, I think then we have to switch departments. You may have to go to the, what are they? Materials? What are they called?
Material science?
Material science, but it's not called that here, is it?
That's
Material sciences. Do we have a department like that? No. Civil and material, that's what it is. Civil and materials. Yeah.
But basically certain objects were collected on this block.
Right, yeah. So I think generally speaking, if it's metallic, like if it can conduct electricity, it will interact with the EM signal and kind of bounce around a little, like there will be some electric field in whatever in this thing, and it'll go off again, right? Something like that. If it's not conductive at all, probably it just goes straight through. I could be wrong. Danilo Ericolo in the EC department, he has spent his career on antenna design. He can probably also tell you a lot about that. All right. Right, so so it's not quite as easy as it first seemed, because there's this, it's not always clear line of sight. If there's something in the way, maybe we can't go through it, but we'll bounce around it, and then all the signals kind of add up in some chaotic mess. And usually, it's not a good thing. Usually, like if you have a clear line of sight, that signal will be very strong. It'll get there first, because that's always the shortest. Right? So it'll get to the receiver first, and then a little bit later, on the order of fractions of nanoseconds later, whatever bounced off a wall will arrive. I don't know if you ever tried like talking loud in a church or something, like a proper church, not one of these ghetto churches, but with vaulted ceilings and stone walls, so it really echoes. Right? It's hard to concentrate sometimes. It's hard to know what you're saying, because you're hearing yourself half a second later all the time. Right? I don't know how they do it, the people at the front. In any case, echoes can be really confusing, and it's really confusing for receivers too, and it's called multipath. One cool part there is that if you have a really poor signal and you're not able to receive anything, sometimes, you may have noticed this, if you just shift your laptop a little bit over, like a half an inch, suddenly it works. It's like that. You can kind of try to rotate it a little bit because, you know, there's no dipole in here, and there's metallic shell of the laptop and all sorts of stuff interfering with the signal. So you kind of change the environment. You can't make it like, you can't plan to make it better. Like, oh yeah, it's got to be like this. But if you try a few different things, suddenly it'll work. Right? You try a few different sort of random random collections of parameters, and it'll work better. This works when you have a really poor signal strength. You run that sort of on a boundary. And the reason for that is this multipath. Yeah?
If you hold command and control on a Mac with the Wi-Fi, it shows you a whole list of, I can't remember which control command.
Anyway, it's hiding in here.
Oh, but you know what I'm talking about? And it'll show you the decibel strength. So you
Oh, I see. Oh, I never done that on the Mac. Okay.
Or maybe it's option. I don't know which one it is. Yeah, that's it.
Ah, cool.
So can you use that to like better your signal?
No.
Or like move your laptop to find.
Yeah, it sometimes will work. Unfortunately, this is a statistical, very crude measure, but it tells you something about how good you can expect this one to be compared to another one. That's the main thing. So here we see my noise is minus 98 dBm, pretty good, right? That's below the usual noise floor. I'm receiving at minus 66 dBm, so only a quarter of a billionth, a 4 billionth of a milliwatt, right? 2.5 times billionth. What is it? No. I don't know how to express these things. Anyway, it's less than a billionth of a milliwatt, right? A billionth of a milliwatt divided by 4. How do you say that? 2.5 10 billionths. There it is, of a milliwatt. Is what I'm getting from that thing. What's that? Quarter billionth? But when it's billionth, it sounds like it could also get bigger when it's a quarter of it, right? I don't know. In any case, I wouldn't worry too much about the signal strength because we're talking about a quarter billionth of a milliwatt. And so for this sort of thing, not a big deal. For this sort of thing, it's different, right? Because now we're transmitting at maybe 100 milliwatt, right? And it's right up against your brain. So, and half of that signal is like going this direction. So that's different than Wi-Fi. People say it is problematic to heat up your brain. I think the sun heats it up a lot more, so I'm not sure. Okay, let's see. Oh yes, and then there's one more thing. And this is sort of stuff that people that design these radio networks need to worry about more than a user, right? But what about when you move? Right. Usually Wi-Fi users are a little mobile, cell phone users are really mobile, and you want to maintain a good Skype connection, right? So what can you do? Well, you can walk close to the Wi-Fi access point and it'll work fine. Right? But what if you want to be on the move, like you want to drive from here to home and you want to have an ongoing phone connection? There's no difference between Skype and phone, same general principle. Then sometimes you're going behind a tree, and then sometimes the tree isn't between you and the antenna again, right? So there's a change here. We're going from good signal to poor signal to good signal as we drive. So if you want to have an ongoing connection, really you have to look at the worst case, right? Because when you're sitting behind that tree, it could be traffic. Now you're sitting behind this tree and it's crap. So you actually also have to take into account this thing called fading. It's basically what it looks like over time. But the signal is good sometimes when you're seeing the antenna, and then it gets bad when you're sitting behind a truck. So, or you're in an elevator. Right? That's terrible. That's a steel cage inside of a concrete building. That's why it never works. Right, so people who design cell phone networks, it's not enough to look at, yeah, okay, free space loss, I'm only a kilometer away from the user, it's going to be totally fine. You have to figure the user is actually inside an elevator a kilometer away. That's the case you have to design for to make it work. That's fading. It's not true if your users aren't mobile. So that's interesting. I think, for example, this new SpaceX satellite network, right? They're planning to do a global internet for everyone with a bunch of satellites, like 12,000 satellites. In their benefit is the fact that they're going to have stationary users. You're not walking around with your cell phone talking to satellites. You've seen those. They're like this, or they're a briefcase you put on the ground, and then you talk with a corded phone to the briefcase. But now if you have a stationary antenna facing the sky with no trees in the way, you don't have to worry about fading. You don't have to worry about what's it called now again? Losses through stuff. Attenuation, yeah, exactly.
What about cloudy day or raining?
Yeah, so they pick a frequency that doesn't get caught by water, and that helps. Right, so they don't need the same link budget that you would need for a cell phone operator, because you don't have to worry about putting the receiver antenna in an elevator. No one's going to do that. They put it on the roof. It'll be fine. Okay, see if I had anything else. Right, noise power. Yeah, we had that here. Noise power, usually, if there isn't anything else, like if there's no transmissions and stuff, it's just like random noise, like radioactive decay and the sun shining and things getting colder. That also emits radio noise. And a thing that's getting colder makes noise in radio and in heat and all sorts. Usually you can figure about minus 100 dBm, between minus 95 and minus 100 dBm. It's just kind of random noise in the air that's always there, no matter what. There's no transmitters in the way. Next time we'll talk about when you have active transmitters. So now we have many Wi-Fi transmitters all over the place, and we want to sort of coordinate so that we don't jam each other's transmissions, similar to in the Ethernet situation. Of course, it's a lot harder in Wi-Fi because everything is moving around, and there's huge differences in power and so on. Okay. There's a brief intro to the physical environment. So next time, Wi-Fi proper, the logical protocol. Time after that, we'll talk about the PHY layer for wireless transmissions to kind of have a rough idea of how radio transmissions actually work. Cool. I will see you on Friday.